Today in this video, we will see numerical. A beam of span 4 meter carries uniformly distributed load of 15 kN meter. The cross section of a beam is this I section. Find maximum stress induced and draw bending stress. See this cross section. Plane side, top plane side 300 mm, bottom plane side 200 mm. Wave height 960 mm, wave thickness 10 mm, top flange thickness 10 mm, bottom flange thickness 30 mm, and beam is 4 meter. Length of this beam is 4 meter. Write in given data. Length of beam is equal to 4 meter. Carries uniformly distributed load UDL is equal to 15 kilonewton per meter. The cross section of the beam, and to find maximum stress. Stress is denoted as sigma maximum stress. So, for solving this numerical, first step is to find position of neutral axis y bar, and after this moment of inertia for this I section, and after this we directly use flexurer formula. M by I is equal to sigma by y is equal to E by R. So step 1, to find position of neutral axis. Y bar is equal to A1 y1 plus A2 y2 plus A3 y3 divided by A1 plus A2 plus A3. Consider this top flange as 1, wave 2 and bottom flange 3. A1, that means area of top flange is 300 multiplied by 10. Y2, mid distance of this top flange from bottom fiber, from this bottom fiber to mid of this distance is y1, and this distance is 30 plus 30 plus 960 plus 10 by 2. $995 mm. A2 is this wave area. Wave thickness is 10 mm and height is 960 mm. 10 by 960, 9600 mm. Here y1, top plane denoted as 1, and y2, wave denoted as 2. Y2 is from bottom fiber to mid of this wave distance. Y2 is this 30 plus 960 by 2, 510 mm. A3 is bottom flange. bottom flange area is this, width of this bottom flange into thickness of bottom flange 200 multiplied by 30 is 6000 mm. And y3 is mid distance of this bottom flange from bottom fiber. This is thickness of this bottom flange is 30 and from bottom to mid distance is 30 by 2. That means 15 mm. Now put this a1, y1, a2, y2, a3, y3 value in this y bar equation. Therefore y bar is equal to 3000 multiplied by 995 plus 9600 multiplied by 810 plus 6000 multiplied by 15 mm divided by 3000 plus 9600 plus 6000. 583.38 mm is position of neutral axis. Calculate this y bar again. A1 y1 is 3000 multiplied by 995 plus A2 y2 is 829600 multiplied by 810 plus A3 is 6000 multiplied by y3 is 15 mm divided by A1 plus A2 plus A3 3000 plus 9600 plus 6000. It's 83.8. Here this is y2 is 960 divided by 2 plus 30. That means this is 5. This is not 8. Plus 960 by 2, 510 mm. Therefore, 3000 multiplied by 995 plus 9600 multiplied by 510 plus 6000 multiplied by 15 divided by 3000 plus 6000 plus 9600. 428.54 is position of neutral axis from bottom tensile fiber. Now next calculate moment of inertia about x-axis axis for this I section. Here, something here. For this, first calculate moment of inertia for this top flange. That means this one. I is equal to I xx1 plus I xx2 plus I xx3. Here I xx1 is this and our position of neutral axis is this. From bottom it is 428.54. x1. So for calculation of this x1 axis I xx1, Moment of inertia for only this top flange is 300 multiplied by 10 cube by 12. Plus because of parallel theorem. Moment of inertia for parallel axis theorem, because of consideration of this whole I section, this I section neutral axis is this from bottom 428.54 mm. So use parallel axis theorem for this. Between neutral axis to this x1 distance, this much distance is this 30 plus 960 plus 5 minus 428.54 mm. 30 plus 960 plus 5, that means 995 minus 428.54 mm is this distance. And area of this top flange is 300 multiplied by 10, that means 3000 mm. First, top flange moment of inertia plus area of top flange 3000 and multiply by original position of this neutral axis to the top flange neutral axis distance and square of this distance for parallel axis theorem. That means 995 minus 428.54. 566.46 and square of this plus wave part moment of inertia is about x-axis is x2 wave is 10 mm thick and 960 mm deep. Therefore, only wave part moment of inertia is 10 multiplied by 960 cube by 12. Plus this wave part area is 10 multiplied by 960, 9600 plus into distance between only wave part neutral axis to the original I cross section neutral axis distance. This distance. That means only wave part neutral axis is 510 and this I cross section neutral axis is 428.54. That means 510 minus 428.54 is 81.46. Distance, this distance is 81.46. Square of this plus bottom flange, only bottom flange moment of inertia 200 multiplied by 30 cube divided by 12. And area of this bottom flange is 200 multiplied by 36,000 and multiply by distance between bottom neutral axis to original I cross section neutral axis. x3 that means 15 428.54 is position of neutral axis for this I cross section and minus 15 That means distance between neutral axis to this bottom plane's neutral axis distance 413.54 mm. Therefore, this I is 200 into 30 cube divided by 12 plus 6000 into 413.54 square plus 10 into 960 cube divided by 12 plus 9600 into 81.46 square plus 300 into 10 cube divided by 12 plus 3000 into 566.46 square. After solving this, moment of inertia is 2.79 into 10 raised to 9 mm raised to 4. Moment of inertia for this I cross section is about x-axis is 2.79 multiplied by 10 raised to 9 mm raised to 4. Now we calculate moment of inertia for this I cross section. We have position of neutral axis from bottom tensile fiber. Now check position of neutral axis from top compression fiber. Which position of neutral axis is greater is important for us because we have to calculate maximum stress induced. So position of neutral axis top compression fiber, that means YC. So YC is equal to total depth of this I cross section is 30 plus 960 plus 10, that means 1000, and minus YT, okay, 1000 minus this YT is, this Y bar is 428.54 from bottom tensile fiber, that means you may also call it YT or Y bar. Y bar is because of I section neutral axis from bottom, and YT is from tensile fiber neutral axis. So 428.54 YC is equal to 1000 minus 428.54, 571.46. This YC is greater than YT, and we have to calculate maximum stress induced, and our maximum stress induced formula is, that means with the help of this flexural formula, M by I is equal to sigma by Y. Sigma max is equal to M by I multiplied by Y. If this Y is maximum, then this sigma is maximum. And this Y is minimum, this sigma is minimum, because sigma is directly proportional to Y. So use maximum value, this value. If you use this 428.54 value, YT value, then your stress comes minimum stress. That's why use this compressive value. Calculation of this YC objective is this. For sigma max, for calculation of sigma max, YC is required. Sigma max is equal to M by I into YC. Our I is 2.79 into 10 raised to 9. mm raised to 4 multiplied by yc is 571.46. What is moment? So see, in numerical they given us length is 4 meter, beam length is 4 meter, and UDL is 15 kilonewton meter. Use simply supported beam bending moment formula. WL square by 8. W is 15 and L is 4 square by 8. 15 into 4 square by 8 is 30. This 15 is in kilonewton per meter, 4 is in meter, that means kilonewton upon 8. That means this bending moment is in kilonewton meter. And we have to calculate this sigma max is in Newton per mm square or in MPa. So this 30 kilonewton meter is converted into Newton mm. That means 30 into 10 raised to 6 mm Newton mm. Because of this, for conversion of kilonewton, multiply 10 raised to 3, and for conversion of meter multiply again 10 raised to 3. That means 30 into 10 raised to 6. Therefore sigma max is 30 into 10 raised to 6 multiplied by 571.46 divided by 2.79 into 10 raised to 9 is 6.14 MPa is maximum stress. Maximum stress in this is 6.14 MPa or 6.14 Newton per mm square. Thank you very much.